lecture on methods for multiple comparisons in statistical tests. So, did you run t-test? Raise your hand. Did you run t-test? T-test, statistical test, one of the statistical tests. No? Yeah. Most of you run t-test. Okay. So, first, let's start from here. X be a normal random variable. Its probability density function follows this equation. This is the equation of normal density function. And so X is a normal random variable. And here, mu is mean, and sigma squared is variance. And assume that you obtained these 9 samples generated from this equation. So x1 to x9 are samples on X. And the sample mean here is 1.815. This is the mean value of these 9 values. So first question here is from this value, the mean value, 1.815. Can we say that the population mean mu of X is not 0? This is a question. So in order to answer this question, we have to carry out a statistical test. We set these hypotheses. One is null hypothesis. It is H0 denote this null hypothesis. The population mean is 0. And the alternative hypothesis, H1, is mu is not 0. Based on this null hypothesis, in this case, here, population variance is unknown. The t-test is the choice. So this is a test statistic, t. T is given by this equation. X bar is mean, and mu is the population mean. And here, V squared is given by this equation. This is called unbiased variance. So here, this value is divided by this n minus 1. This is the unbiased variance. And n is the sample size. This is a snapshot of Excel file. So please open this Excel file, name this one. Please open this one. I sent the file yesterday, so please open this file. One t-test, one group. Do you have that one? Do you have the? If you do not have that Excel file, okay, please open the Excel file. Here, this one. And open this one. And here, I left these cells vacant. So please fill these cells. The answer is written on the slide. Every answer is written on the slide. So you can just input those equations in each cell. So this exercise is just for your experience. Some of you are not familiar with Excel, so this is just a practice. Okay, let's wait a few more minutes. Okay, let me explain this slide. This shows that these 9 samples are obtained, and you calculated sample mean and unbiased variance, and this is the test statistic given by this equation. And the p-value. This is later I'll explain this function, t-dist function, with more in detail. And here the if function check that this p-value is significant, statistically significant. And in this case, this p-value 0.043 is less than the threshold. Threshold is set here, 0.05, and this is smaller than this value, 0.05. The answer is yes, this is statistically significant. And so the answer to Q1 is here. The population mean is not 0. The question here is this one. 1.815. Can we say that the population mean mu is not 0? And this null hypothesis is rejected, and we accept this one, alternative hypothesis. Which one? This is t-test. So let's move on to the next simulation. Later I'll go back to these questions. And first, I'd like you to do another writing of Excel files. So please open this one. 3, simulation of t-test, 1 group. Please open this Excel file. Number 3 file. In this file, these cells are not written. Just I left these values meaningless. So please input the equations in each cell. The answer is written on that slide. If you do not if you are not familiar with Excel file, then the explanation how to input those equations are given in the next 2 slides. So you don't have to write before or the cell numbers. Just click the cell where which you want to input. Page 10, you'll see the explanation how to input those cell numbers. Also, cell 11, you'll see how to copy the equations. After you finish inputting those equations, push F9 key. For Windows, push F9 key. But if your computer is Mac, F9 key, maybe FN F9 or Control equal key. If your computer is Mac, Windows, F9 key, push F9 key, then all the cells are recalculated by pushing F9 key. And you experience the t-test again and again. In each cell, the normal random variables are generated. When you push F9 key, and every time you experience t-test. And 5 out of 100 times, you will see that this number becomes 1. Okay? Every time you generate 9 samples, and this sheet carries out t-test. Did you finish this one? Okay, raise your hand. Okay, okay. Let's move on to the next practice. Open fourth Excel file. This one, 4. Simulation of t-test, one group, 1,000 repetitions. Open the fourth Excel file. So this is a file I prepared. And these cells generate 9 samples and calculate the t-values and carries out t-test. So I'd like you to copy these cells. Do you know how to copy this one to the next column? Drag this part. Then all the cells are copied. Click here. So this cursor, the form of cursor is changed to cross. Then click left button of mouse and drag it to the right. Then you can copy all the cells. Here you see that first, second, third, automatically this number is changed. Okay? And drag to the right, and you see this number until this becomes 1,000. Please copy those columns. After that, change this equation here. The answer is written on the slide. this should be ALM, 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 ALM. Yeah, ALM. Change the equation in this cell from B20 to ALM20. The answer is written on the slide. The slide page is 13. And push F9 button. All the cells recalculated every time you push F9 key. And you see that this number fluctuates around 0.05. Okay? So time is limited. So let me explain the slides one by one. And now you are ready to listen to my lecture. So you inputted these equations here. So please go back to page 4. Fourth slide. And you carried out t-test. So the question here is, first is t-dist function. You inputted this function. This is an Excel function. And you can go to this URL, the Microsoft Office Excel support page. Then you will see these explanations about t-distributions. This function returns the percentage points, the probability for the student t-distribution. X is here, this is a t-value, and degree of freedom. Here, this is sample size minus 1. So in the case 9, there are 9 samples. This is 9 minus 1, so this is 8. And two types of tests. There are two types of tests. One is one-tailed test, and the other is two-tailed test. So you inputted this too, so you carried out two-tailed test. So the next question is, why is t-test employed? And you simulated this t-distribution. Excuse me. This is the Excel sheet I programmed, and I didn't explain this one. Let me show you this slide. Also, you can open the slide, open the Excel file, number 2. This is to simulate t-distribution. Now, you can understand what these cells calculate. These generate normal random variables and calculate the t value. This is a t value. And this here is a t value. This t value is rounded off to 0 decimal place. So minus 0.2 becomes 0, and 1.6 becomes 2. And in these cells, this cell counts how many times -5 occurs in 1,000 simulations. So this means -5. There's 1 -5, and there are 2 -4. And this shows the histogram of these values. So the 0 occurs many times. And -5 occurs just one. And the red histogram is a theoretical value of T distribution. So if you push F9 key, blue bar fluctuates, but it is around the theoretical value. So this T value follows T distribution. Now you can experience the T distribution. It's better to fix the maximum of the vertical axis. This is better. You see that the blue bar fluctuates around the theoretical value. So the T value follows T distribution. This is an empirical reason why that T statistic is used for the T test. Okay, please look at this slide, page 8. This is the T distribution. The degrees of freedom is 8. And if the T value is 2.396, this means that here, the probability that the absolute value of T is over 2.396 is 0.042. So this area, this is the probability density function. And this area means the probability. So this blue area, and the summation of these two blue areas is 0.043. So when P value is this one, this area, 0.043. So if the null hypothesis, mu equals 0, is true, and the probability of T equals 2.396 is very rare. But you actually have that data. This means that the hypothesis, null hypothesis, H0, mu equals 0 is wrong. And so the alternative hypothesis is accepted. This is a T test. Next question is, what is type 1 error? Do you know type 1 error? Did you learn type 1 error? Did you learn? Okay. So you inputted equations in this sheet, and you generated normal random variables, and you carried out t-test at every time when you push F9 button, F9 key. So in this, let me go back to this. In this simulation, these random variables are generated based on this one, mu equals 0 and sigma equals 1. This means that the H0 is true, you obtain 9 samples. These are generated from this u equals 0. So H0 is true. But sometimes the p-value becomes very small and less than 0.05. In this case, H0 is rejected and H1 is accepted. But these samples are generated from this one, based on this one, mu equals 0 and sigma equals 1. This means that the H1 is falsely rejected, even though H0 is true but rejected. So this is called type 1 error. And this value, 0.05, is empirically decided. There's no theoretical reason why 0.05. You can choose 0.05 or 0.01. And this is called significance level. And alpha denotes this significance level. There is another error, type 2 error. This is H1 is true. So the samples are generated from the source that have the different value than 0. Mu is different. H1 is true, but not accepted. This is also happens. So this is called type 2 error. So you also inputted these cells and you carried out 1,000 times of t-test. And you obtain this frequency of type 1 error. This is type 1 error. You see, this is around 0.05. This means that 50 out of 1,000 type 1 error occurred. Almost I should stop my today's lecture. But the main theme starts from now. The main thing is one of the cases is here. There are two groups. One is here, and the other is here. These are samples, and both two follows normal random variables, and x1 and x2. These two are independent. So if you set these hypotheses, first group, null hypothesis, mu1 equals 0, and alternative hypothesis is mu1 not equal to 0. And for the second group, the same kind of hypotheses are set. Then, if you carry out the t-test, this is also another t-test. Next time, I'd like you to do practice and study more about the multiple comparison. This is not multiple comparison, just, excuse me. This is multiple comparison. So each test, this is the first group, and this is the second group. Each test, the type 1 error is kept at 0.05. But this error, this is called family-wise error rate. So this means that 103 out of 1,000 simulations, type 1 error in either of these two or both occurs. So in the case of multiple comparison, in the case if you do t-test 2 times in your paper, if we want to write a paper and submit it to the society, one of the societies, if you carry out 2 t-tests, then the probability that the type 1 error occurs in either of these two or both becomes larger than 0.0. here FWR is 0.103. This is larger than 0.05. So let me finish my today's talk here. So it is more probable than 5% for you to reject one of null hypotheses. This is lucky for you, because you want to reject one of those hypotheses. You want to prove that my method is better than the other one, the conventional. But if you write a paper based on this result, your paper will be rejected. Okay? Be careful about the multiple comparison problem. This phenomenon that FWER is larger than 0.05 is called multiple testing problem. This is very serious problem and difficult problem. In many papers, some researchers do not understand what is multiple comparison. Also, reviewers do not understand what is multiple testing problem, and they accept these papers. So you'll see some papers did these mistakes. So next time, I'd like you to experience the multiple comparisons and how to cope with this multiple comparison. Okay, thank you. Next time, I'd like you to do some homework. Next time, not today. James, hi.
So for today's lecture, please write.
Hi, good morning. Let me restart my talk from this slide, on page 15. So we assume x1 and x2. These are normal random variables. And these two variables are independent. And their probability density functions are given by this equation. So the x11, x12, and x1n are samples on x1, and these are samples on x2. And we apply t-test to each group, group 1 and group 2. So the null hypothesis is this one, h10 equals mu1 equals 0. And alternative hypothesis, h11, mu1 not equal 0. On the same type of hypothesis, we have these hypotheses. And if we apply t-test independently to these groups, what will happen? This is a question. And the file, this one, the name is 5, simulation of t-test, 2 groups, 1,000 repetitions. Please open this file. So in this file, the t-test is applied to these groups. This is the group 1. There are 9 samples, and these are normal random variables, and sample mean. And this is the other group, and this is the sample mean. The t-test is applied to this mean value. And this is the t-statistic. And this is the other t-statistic. And the p-value is obtained based on this t-statistic. And if this is smaller than 0.05, then the type 1 error occurs. So it is judged that type 1 error occurs. So, and this number becomes 1. And this here, this is to check whether one of these values is 1. If one of these or both are 1, then this value becomes 1. This means that the type 1 error occurs in either of these two groups. And this test repeated 1,000 times. So you'll see these groups, 1,000 groups in your file. You see 1,000 groups, and in each group, t-test applied 2 times. And if you push F9 key, if you push F9 key, all the variables are regenerated, and the t-test are applied, in this case, 2,000 times. This way, here, the p-value is smaller than 0.05. So in this group, type 1 error occurs. Also in this group, also type 1 error occurs. So in these two groups, type 1 error occurs. So this becomes 1. Like, and if you count this row, the number of 1 in this row, okay? This is called family-wise error rate. Family-wise error rate. It becomes larger than 0.05. So this 1, and the number of 1 in this row is 69. Among 1,000, 69, there are 69 1 in this row. If we push F9, you'll see another values. Every time the random variables are regenerated and the FWER changes, and it fluctuates. So question here, what is the average of FWER? What do you expect the average value of FWER? It fluctuates. But you can expect the average of this FWER. What will be the average value of this FWER? Approximately. Yeah, 0.1. Yeah, approximately 0.1. Okay, let's move on to the next slide. Page 17. FWER is called is family-wise error rate, and this is the probability of making one or more type 1 errors. So in the previous slide, in your simulation that this FWER is approximately 0.1. So if we repeat t-test 2 times in one experiment, so in your paper, some of you will do t-test 2 times in one paper. This is the case. In this case, the probability of type 1 error will be approximately 0.1. I made a mistake. This is 1 in your manuscript, but this should be 0.1. Okay, page 17. This value, I made a mistake. This should be 0.1. And it is larger than 0.05. So the type 1 error should be kept lower than 0.05. Because this is the error. Because there is no difference of the mean value. It should be 0. But the 5% error chance rate, we have to accept this type 1 error. It should be less than 0.05. If it is larger than 0.05, it is not good to accept the result. But in the case of this case, you apply t-test 2 times, it becomes larger than 0.05. And so this may be lucky for you because you want to reject the null hypothesis. But you are right, as I said before, that if you write a paper based on this result, your paper will be rejected. FWER should be kept less than 0.05. So this phenomenon, FWER is larger than 0.05, is called multiple testing problem. Let's move on to this slide, next slide, page 18. So how can we cope with multiple testing problem? The theoretical probability of FWER in the case of X1 and X2, the t-test applied 2 times. This is, in each t-test, the type 1 error is kept 0.05, less than 0.05. If it is kept 0.05, then the alpha here is 0.05. But the 1 minus alpha means that type 1 error does not occur in one test. And in 2 tests, both tests, the type 1 error does not occur. It's this value, 1 minus alpha squared. So if 1 minus this value means that FWER, one of the groups, or in both groups, the type 1 error occurs, that probability becomes this one, 0.095975, approximately 0.1. So it is larger than 0.05. So if you want to make this value, FWER is equal to 0.05, then this alpha for each test, it is denoted this value, alpha prime. So alpha prime is obtained by changing this equation. And this is 0.05. Family-wise error rate should be kept equal or smaller than 0.05. So that in each test, this alpha prime is given by this equation. This is called SYDAC correction. This is the person's name, SYDAC. So another correction is Bonferroni correction. Because this idea was presented so many years ago, 30 or 70, 40 years ago. At that time, there's no calculation machine. So it's difficult to obtain this value. This is not so difficult root, but if if there are 3 groups, then this becomes 1/3. Then it's difficult to calculate this value. So this is convenient. This is called Bonferroni correction. So if the t-test applied 3 times, then this becomes 3. If it is 4, then this becomes 4. It's very convenient. This is called Bonferroni correction. Simple homework. Simple homework. Prove this inequality equation. Very simple homework. Okay, please open this file, 6. In this cell, this significance level is made vacant in this file. You see this one. Number 6. See. In this file, please open this file, and in this file, this cell is made vacant. So you can input the equation, that's the correction, into this file. Then you'll see that FWER is kept equal 0.05. In order to input the equation here, double-click this cell and write the equation this way.
Maybe the power there is what, 1 or 2?
This one? Yeah, 2.
2.
Yeah.
Because I see in the slide. In the slide.
Slide?
See that function?
Oh, excuse me, I made a mistake. No, this one, not this one. Excuse me. Yeah. Okay, and then this corrected significance level is applied to each t-test. There are 2 groups. So, for example, here, there are 2 groups. And each t-test, that corrected significance level is applied. So the FWER here, the average value becomes 0.05. If you carry out t-test 2 times in your paper, then in each test, the significance level should be corrected. It should be made smaller than 0.05. In this case, it should be 0.0253. Otherwise, your paper will be rejected. If we apply Bonferroni correction, then the significance level is more strict, and that value is smaller than 0.25, and the test becomes severer than SYDAC's correction. But it's very convenient to apply Bonferroni correction. Okay, let's move on to one of the most popular statistical tests. So there are two random variables, two sets of random variables. These two sets are generated based on normal random variables, normal distributions. And these two variables are independent. The hypothesis is different. Here, the null hypothesis is this one, mu1 equal mu2. And alternative hypothesis is mu1 not equal mu2. This is more popular than the previous test because this is the data from your proposed method. These are the data from the conventional method. You want to compare the performance of the proposed method. This is a more popular case. My method is better than the conventional one. So this is the null hypothesis. You want to reject this null hypothesis because you want to prove that your method is better than the conventional one. You want to accept this alternative hypothesis. This is a setting of the t-test. This is another t-test. So this is not multiple comparison, just a usual case of the comparison of these two means. So please open this one, 7. And some of the cells are left vacant, so please input those cells. The equations are given here. Do you have the material?
Oh, yes, I have it.
Ah, okay. If you succeed in inputting the equations correctly, then you see that by pushing the F9 key, approximately 5 times per 100 simulations, then this becomes 1. This is type 1 error. It is a rare case that this type 1 error occurs, but sometimes it occurs. This occurrence rate is kept 5%. Okay, time is limited, so let's move on to the next slide. In this case, these mean values are said to be equal. We cannot say that these mean values are not different. So the answer to the question 8 is this one. So in the Excel, this function is available, tdis. This is a t statistic, and this is the degrees of freedom. This degrees of freedom is given by this one, 2n minus n. N is the sample size. So please open this file, number 8. And push F9 key. The average of this occurrence of type 1 error is 50 among 1,000 simulations, 5 among 500 simulations. This is not a multiple comparison, just a comparison of two groups. Then next, this is the case that we should consider multiple comparison. So there are three groups. One of the cases you have is that you invented two methods. You want to propose two methods. One is this one, and these are the data from method 1, and these are the data from method 2. And group 3, this is the conventional method, the data from conventional method. So which is better? You want to compare these three groups. The question 10 is that can we say that there is a difference, or there are differences in the population means mu1, mu2, mu3 of these data. So the null hypothesis is this one, mu equal mu and alternative hypothesis is mu not equal mu Again, you want to reject one of or two of these hypotheses, and you want to accept the alternative hypothesis. Please open file number 9. You don't have to input any equations, any new equations, all are inputted. So you'll see that by pushing F9 key, in this cell, the FWER is calculated. The type 1 error in one of the t-test occurs or not. It's indicated in that cell. Also, in the file number 10, this test comparing the mean values of each group. So in this case, the comparisons are made 3 times. And this t-test repeated 1,000 times in this file, number 10. And SystemⅠ correction is applied here. So the t-test is applied 3 times. So this correction is given by this equation. This is 3. And this is the family-wise error rate. If you push F9 key, this value changes and fluctuates. And it looks like it is kept approximately 0.05. File number 10. Again, you don't have to input any new equations in this file. And by pushing F9 key, this FWER fluctuates. So how much is the average of this FWER? So I wrote a macro. In this file, this is a XLSM file. This means that macro is included. And I programmed a macro. You can open this macro. So this is Japanese. So if you want to open the macro, click developer and macro, and you'll find the file, confidence interval, and click the edit button. This is the macro I programmed. This macro is just to read this value in this cell, FWER, and read this value and write the same value here, and recalculate all the tests and obtain the new FWER and read that one and write that value to the next cell. And this is the average. This FWER is calculated 100 times. And this is the mean value of these each FWER. So it is less than 0.05. And you can calculate the 95% confidence interval of FWER. This is the mean value, and this value fluctuates. Then you can obtain this confidence interval range. So the true FWER is probably in this range. This means that the SYDAC correction is severe. The obtained FWER is less than 0.05. The multiple comparison is a very complicated problem. So let me explain why the SYDAC correction is severe, and it should be eased a little bit to make the FWER 0.05. Let me just briefly explain why it happened. This is the case that T1 and T2 are independent. These are the test statistics of T statistic. And these two are independent because here x1 var and x2 var, average of x1 and average of x2. These are not included in the same equation. These are separated. These values are independent. But in the case of this one, x1 and x2 appear in this equation. Also, x1 appear in this equation. So these two are correlated because x1 is included in both equations. So this is the probability density function So if these two are independent, then this contour is not related. So this axis and this axis is parallel to this T1 and T2. But in this case, these Q12 and Q31 are correlated. Then this long axis of this elliptic is not parallel to one of these axes. Then this area, colored black, the probability in this area is the family-wise error rate. It extends to the infinite space. So, so in this black area is equal to the FWER. But in this case, it should be the absolute value of this threshold level is made smaller than this one. Then this black area becomes 0.05. Because of this shape, it is concentrated more to the center. So this threshold can be made narrow. Tukey, the person his name is Tukey. He obtained this equation. He derived this equation, and this cannot be solved analytically. So he made a table, and this is a table. Okay, Tukey obtained a table of threshold of Q value. And in the case in Excel file number 10, t-test applied 3 times. So there are 3 groups. Number of groups is 3. And the degree of freedom is 24. There are 9 samples in each group. So 3 times 9 minus 3 is 24. So the degrees of freedom is 24. In this case, the threshold value is this one, 3.532. And this value should be divided by this one, root 2. This is just Tukey's choice. From this table, you obtain this value, 3.532, but it should be divided by root 2. So this is the threshold. This is a little bit larger than the Statistical correction. And the value on this table are called studentized range. Very strange name, but Tukey named this table studentized range. So please open the last file, 11, and input this one, this threshold, 3.532 divided by root 2. Then the family-wise error rate is kept almost equal to 0.05. you can execute macro, and you'll obtain new confidence interval by clicking this button. Then you can recalculate this interval range. Every time the true FWER is in this range, 0.05. Okay. So if you want to compare your method to the conventional ones, you should be careful about the multiple comparison and remember the name Tukey. Okay, that's all. Yeah.
And how many samples do we need to test? Because if there might be degree of freedom, so what would be a good selection for degree of freedom?
The larger, the better. But in some experiments, you cannot obtain so many data. Then it's okay if you have only 5 samples. Then from that table, you can derive the threshold level. Then you can check that one.
If you have to compare our method to the conventional method, why should we set the number of tests to 3? Because one of them is already for conventional. So why don't we use 2?
It depends on what you want to verify, what you want to check the performance of your method.
So that means if we have, for example, 4 or 5 proposed methods, then we need to use 5 or 4 accordingly.
Yeah.
How about noise?
Noise?
Yeah.
Yeah.
Can this method tolerate noise?
So noise is included in these values. So yeah, these are random variables. So the average value and around the average value, the noise is included. So the obtained results fluctuates around average values. Yeah. Because noise are included, so you should do statistical test. If you have only 5 data, then you have to check statistically it is different or not. If you have 100 data, then maybe probably it's not necessary to apply a statistical test because the average value is more reliable than the case that have only 5 data.
So if the number of samples is too few, then we have to do all this stuff in order to make sure that our hypothesis is okay.
Mm-hmm.
So that means if the number of samples is large, then we don't need to do these statistics.
Yeah, if you have 100 samples,
Then we don't need.
Well, I'm not 100% sure.
But I mean, let's just assume that we have 100 samples. Then we don't need to do all these things for the experiment.
Yeah, probably. But if that difference is very close, and the variance, it fluctuates more than the difference, then you need to apply to do statistical test. If the averages are very apart, different, and it fluctuates, this one and this one, then you don't have to do statistical test. Okay.
So you are saying that the noise is included in the random variable.
Yeah.
But as in the Excel files, the sample is follows a distributed functions as far as I. So how if the random variable don't say follow the distributed functions?
Excuse me.
So the samples you have a assumption that the samples data follow the distributed functions.
Yeah.
Yeah. So
Yeah.
how if the samples?
Yeah,
does
good
not?
question. So this Tukey test is based on the assumption that the data, the noise, noise follows the normal distribution. This is a basic assumption. So if the noise does not follow normal distribution, you should apply a non-parametric test, non-parametric statistical test. This is one of the parametric statistical tests.